Black holes are very powerful celestial objects. We cannot see them directly because they're completely black. However, it doesn't mean that we cannot detect their presence. In fact, when two black holes merge, they send out strong signals in the form of gravitational waves. In this presentation, we're going to see how to detect binary black hole mergers. The presentation will be broken down into 4 parts. So we're going to start with an introduction to black holes, then we're going to see how black holes merge, and then we're going to go to gravitational waves, and finally how to detect the gravitational waves. So a black hole is a very massive object that has zero volume and infinite density. You can picture it as a region in space-time where the gravitational force is so strong that even light cannot escape from it, which is exactly why it appears to be black. Gravity is so strong that it collapses matter into a single point at the center of the black hole, which is called the singularity. Just to give you a sense of how high the density is, if I could compress the Earth to the size of a sugar cube, it would become a black hole. At this point, gravity takes over and it would compress it even further. So if matter is compressed into a single point, what is the size of a black hole? Well, the black hole's size is determined by its event horizon, which is a sphere around the singularity. And the radius of the sphere is called the Schwarzschild radius, which is given by the equation r equal to gm over c squared, where r is the Schwarzschild radius, g is the gravitational constant, m is the mass of the black hole, and c is the speed of light. Once inside the event horizon, nothing can escape because the required escape speed is greater than the speed of light, and of course, nothing can go faster than the speed of light. Now that we know what a black hole is, we can now look at how two black holes merge. So first of all, for obvious reasons, the two black holes have to be relatively close to one another. A binary black hole system is exactly what we're looking for. Since black holes have an incredibly high gravitational force, we would expect them to merge very quickly. But in fact, the process of merging is actually very, very slow. In a binary black hole system, the two black holes orbit around each other. In the process, they lose energy in the form of gravitational waves. As they lose energy, their orbit becomes smaller and smaller. In other words, the black holes get closer and closer to one another. Again, this is a very slow process. After billions of years, the two black holes finally get close enough and merge. The product is a single, more massive black hole. So here is a short video just to help visualize. And of course, what you see now on the screen is not filmed. It is a simulation, and we can detect binary black hole systems because of the gravitational waves they're creating. So now let's see what gravitational waves are. So gravitational waves are disturbances in space-time. They're electromagnetic waves, so they travel at the speed of light, which is 3 times 10 to the 8 meters per second. Gravitational waves propagate very similarly to how a wave propagates in water, except that they propagate in space-time and they are much faster. They carry energy in the form of gravitational radiation. When a gravitational wave passes through an object, it compresses and stretches that object, creating distortion in the object's shape. Gravitational waves are constantly passing Earth, but how come we don't feel anything at all? This is because their source is very far away from us, and by very far away, I mean hundreds of millions or even billions of light years away from us. A reminder that 1 light year is approximately 9.5 times 10 to the 15 meters. So even though gravitational waves are very powerful, by the time they reach Earth, their effect is very tiny. And the effect is so tiny that if a gravitational wave hits a 4 kilometers long object, it will change its length by roughly 0.001 times the width of a proton. So how do we detect those waves? In order to detect those tiny distortions, we need an extremely sophisticated device such as LIGO. And the LIGO, the full name is Laser Interferometer Gravitational Wave Observatory. So let's see now how LIGO works. Here's the basic idea. A laser is shot from the laser source. When it reaches the beam splitter, the light is evenly distributed into each of the two orthogonal arms. Then the light reaches the mirror at the end of an arm, and it bounces back towards the beam splitter. And at the beam splitter, the two laser beams recombine, and the combined signal is sent to the photodetector, which is the black dot right here. The two arms length, when the two arms length are equal, the beams are almost out of phase, resulting in only sending weak signal to the photodetector. When the gravitational wave passes, the arm's length are slightly distorted. The shorter arm returns the beam slightly faster than the longer one. With repeated contractions and elongations of the arms, the laser beams create an interference pattern, which is then recorded by the photodetector. And this is only the basic setup. If LIGO were only like this, we wouldn't be sensitive enough to detect gravitational waves. So in order to increase the sensitivity, we need to make the arms longer and make the laser more powerful. And this is how we do it. So the distance problem can be solved by implementing Fabry-Perot cavities. As you can see in the picture, instead of only having one mirror at the end of an arm, an additional mirror is placed near the beam splitter. Basically how it works is that after the laser is split at the beam splitter, the beam bounces between the two mirrors about 300 times before recombining with the other wave, with the other beam. So the light, instead of traveling for 4 plus 4, 8 kilometers, it travels for 300 times 4, so 1,200 kilometers in total. The Fabry-Perot cavities significantly increases LIGO sensitivity, as the longer an object is, the greater the gravitational waves affect its length. So the increase in length amplifies that effect. Now let's take a look at how to make the laser beam more powerful. The laser coming out of the source has a power of about 40 watts. In order to detect gravitational waves, LIGO needs to operate at about 750 kilowatts. So how do we amplify the power of the laser beam? The answer is by using a power recycling mirror. The power recycling mirror is a one-way mirror. It means that light can go through it from one side, but it's reflected on the other side. Essentially what happens is the laser beam passes through the power recycling mirror and goes to the beam splitter. At the beam splitter, the laser beam is split evenly into the two arms. And on the way back, so the laser beam reflects on the mirror here, and on its way back, it's reflected by the power mirror again and sent back into the arm. And basically this recycles light. The laser source here, continuously sends power into the arms, and the mirror, the power recycling mirror, continuously reflects the beams back. And this process greatly amplifies the power of the laser beam. And this increases LIGO sensitivity because the more powerful the laser beam is, the sharper the interference pattern is. And with the help of the Fabry-Perot cavities and the power recycling mirror, LIGO is able to detect changes in length of about 0.001 times the width of a proton, which is approximately 10 to the negative 19 meters. So LIGO's first detection of gravitational waves was back in 2015 on September 14. The gravitational wave signal was named GW 150914, which basically stands for gravitational wave 15 September 14. The source of those gravitational waves was a merging binary black hole system 1.3 billion light years away from us. Before the merger, the black holes had respectively 36 solar masses and 29 solar masses. After the merger, the combined black hole had a mass of 62 solar masses. And during the merging process, 3 solar masses c² joules of energy was released in the form of gravitational waves. So that was the first ever direct detection of gravitational waves and observation of a binary black hole merger. To wrap it up, a black hole is a very massive object that has no volume and infinite density. When the two black holes merge, they send out strong gravitational waves, which are essentially ripples in space-time. When they pass by Earth, they cause tiny distortions in the dimensions of objects. LIGO is able to detect those tiny distortions by recording the interference patterns created by the laser beams. And by analyzing the interference patterns, we can get information about the source of the gravitational waves. Binary black hole systems are not the only celestial objects that create gravitational waves. In fact, remnants of primordial gravitational waves produced by the Big Bang still exist today. So maybe you could know more about the origin of the universe by detecting and analyzing those waves. So this is the end of the presentation. Hope you enjoyed and thank you for watching.